Okay, hi everyone. I'm Eleanor. I'm a software developer at Salesforce, and today I want to talk to you about how we develop AI applications for businesses at massive scale. So we don't just develop any AI application, we develop turnkey AI applications. What is turnkey AI? So what it basically means is that the customer doesn't have to do anything for the AI to work. At the press of a button, the AI starts executing and start generating different insights and predictions for the customer. So for the customer, these are good news because it's easy to deploy and the customer doesn't have to hire a team of data scientists to develop a solution for him. He just enables the flow and the AI starts to work out of the box. But for the providers, for us, it's a pretty challenging task. We have to provide an accurate solution for all our customers. And we're not just providing any turnkey AI application. We need to provide an AI application that works on customer data. So we don't own the data. We have no control over the data. And the application has to work for all our customers, regardless their data. And we also, obviously, need to scale. We need to handle large volumes of data. So that's a pretty challenging task. And before I start describing the different challenges and how we tackle them, I want to give an example of a turnkey AI in Salesforce, Einstein lead scoring. So you've probably all registered at some point in a site like Amazon or Alibaba or some other site. Not all of us are aware of that, but when we register in these sites, we actually become leads. We are registered as leads in Amazon and Alibaba and other sites, and that way, Amazon, for example, knows they can target us. We become a target. So we are all leads in different lists of leads somewhere, and we're not even aware of that. So there are actually sales teams working with large lists of leads, hundreds, thousands of leads, and their goal is to actually convert these leads into deals that they can close when they actually sell the product. So how does a sales rep working with these long lists, how does he know where to start? Which lead to contact first? So Einstein lead scoring actually gives a score to each lead, and not only it gives a score, it also explains the logic behind the score, the reasons why this score was given to this particular lead. The score is given according to the likelihood of this lead to convert to a deal. So now the sales rep, all he needs to do is basically sort the list, start with relatively high scores, leads that have potential to convert to deals. So this is an example of a turnkey AI in Salesforce. The customer enables the lead scoring flow, doesn't have to do anything, doesn't have to configure anything, and it just works out of the box. So what kind of challenges are we dealing with in scaling turnkey AI applications? There are many challenges. I'll only mention a few. So first of all, we have many different customers, small, medium, large enterprise customers, and this introduces different challenges. Small customers, from an engineering perspective, it might be easier to start with small customers because they don't have much data, so the data fits into memory. There aren't many performance or memory usage concerns. But from an AI perspective, they might not have enough data to train good models. For large customers, it's completely different because the data is more complex. They usually have different business units, different teams, and we also need to handle that. For example, Dell can have a team selling laptops and a different team selling storage units. These two teams work completely different. They have different leads data, and we need to think about it when we provide an AI solution for them. And we'll see how we tackle this challenge later on. Another challenge that we have is competing with in-house solutions. So some customers have their own in-house solutions. They obviously have the home advantage, right? Because they know their data best. They can have a tailor-made solution that is tailored to their needs and to their data. And they also get constant feedback from their sales reps. We can't do that. We can't tailor the solution to a specific customer. Remember, we're actually developing turnkey AI solutions. They should work for all our customers, regardless their data. So we can't tailor the solution, and that's pretty challenging. We have to make it work for everyone. And we've actually seen many examples where the turnkey solution worked better than the in-house solution. Another challenge that we have is the trade-off between accuracy and performance. So we could train thousands of models in production and use thousands of different features and increase our sample size. And by doing that, we increase the accuracy of our model, right? But our application won't scale. It won't work. It will be extremely slow. Our memory consumption will be extremely high. And we can't really do that. We have to find a good balance between the two, between accuracy and performance. So we've mentioned a few challenges. How do we tackle these challenges step by step? So first we have to cover the basics. In any application, not just AI applications, when you want to scale your application, you need to think of a large-scale architecture, a caching mechanism, parallelism, code optimizations, whether you're working with Python or any other language for that matter, database optimizations, network optimizations, and the list goes on. But maybe the most important thing in the list is testing and monitoring. Testing and monitoring is crucial. And we use tools like Datadog, which you're probably familiar with, Splunk logs, and other monitoring tools. Obviously, you also need performance tests in place, accuracy tests in place. And once you have the basics covered, how do you actually scale your AI application from the AI perspective? How do you do that step by step? From collecting the data, through training, through the prediction phase, and finally the evaluation phase. So let's start with the collect data. When we get the data, when we first collect the data, we only get the deltas. When we get leads, we only get new and updated leads. We don't need to refetch the data all over again. So that's one very simple optimization. We also fetch the data in batches. And think about it, we can have millions of leads. We don't need to use all these leads, and we can't really use all these leads in training. So we sample the data. And finally, we also clean the data. We allow the customer some level of control, and the customer can actually exclude certain fields or filter certain leads that he doesn't want to get scores. And this is called field exclusion and row level filtering. Moving on to the train model phase, you have to decide on the retrain times. When do you really need to retrain your models? How frequently do you need to do that? And if it's not as frequent as providing the predictions, a good idea would be to separate between the two, between the training and the prediction. And we do that. We have different flows for that. How do you select a model for all your customers? Do you use the same model for all customers? So we'll see how we tackle that later on. What about feature generation and selection? So you can actually use rare values and top values and reduce the number of features, and that way you use only meaningful and interesting features that can really help your model and improve your model results. Moving on to the prediction phase, when we score our leads, when we provide the prediction, we do that in parallel. And again, we upload the results in batches. And when you upload massive amounts of data, you have to have a retry mechanism in place because there will be failures. It won't work if you won't have a retry mechanism. Finally, in the model evaluation phase, you need to think of evaluation methods. Do you use the same model and the same method for all your models? Obviously, each model maybe you have a different way of evaluating it. So you need to take that into account. You also need to have a dashboard, like a single view where you can track your model, see how your model is doing, how it's doing over time, view different trends, aggregate results across different customers. And again, testing. Testing is important, so you should have accuracy regression tests in place. You can actually have a test that checks if your model is not accurate due to code changes. Maybe it can prevent deployment. Or if your code is executing longer than expected, again, you can prevent deployment. So let's see some, after we've seen like a high-level description of how we can handle that and how we can scale our code in each step, let's see some concrete examples. So the first example is related to the collect data phase. So some of our features use emails data and analyze emails data to create different insights. The emails are actually stored in Amazon S3, online object storage. And the emails that we've already fetched from Amazon S3 are stored, only their keys are stored in a Mongo collection. So the emails flow goes as follows. We first get the list of emails stored in Amazon S3, just the keys, and then we match them with the emails that we have in our Mongo collection. And we see which emails we need to fetch, which emails are new and we don't have in our Mongo collection, and we need to fetch them from Amazon S3. So we've noticed in our Datadog dashboard that this flow took us longer than we would expect. And investigating this issue, we found that the bottleneck was actually the matching phase, matching the emails from Amazon S3 to our Mongo collection. And the matching was processed in using a Python threads. And the global interpreter lock in Python was actually the root cause for this issue. So the global interpreter lock, the GIL, prevents Python threads from executing Python code at the same time. But when a thread is waiting for an I/O operation, for example, then a different thread can take over and continue its execution. The developer that chose Python threads in the implementation here had an assumption. He assumed that most of the time would be spent on I/O operations. But actually, that wasn't the case. Most of the time was spent inside the GIL, matching emails in memory between the Mongo collection and S3. So the solution here was to replace the threads implementation with celery tasks. And this actually decreased our processing time from over 100 minutes to 20 minutes. This was a major decrease in processing time. So obviously the conclusion here is to use Python threads cautiously, but also to monitor your code so you will be able to detect these bottlenecks and later solve these issues when you encounter them. Another example in the collect data phase is the enrichers example. We actually have enrichers in place that enrich the data. When we get the leads data, we add more new and interesting features over the data. For example, we have the phone validity enricher that adds whether a phone is valid or not. And this enrichment work takes time. The execution takes time. The problem was that the enrichers were part of the training, so it increased the training time significantly. So what we did, we actually moved our enrichers logic outside of the training. So it's really important to decide when you're going to do which job. If it takes longer, if you can separate between these jobs, it's a good idea. You don't have to enrich the data after training. So if previously, every time we retrained, enrich was triggered, now enrich is triggered once when we collect the data only for new and updated leads. That way, the training flow gets the leads already enriched, and that saves us a lot of time. Moving on to the training model phase. So how do we select a model? Do we use the same model for all our customers? So the answer is no. We can train multiple models for each customer. We evaluate each of the models in production, and we choose the best model. We choose a winner for each customer. So for example, in this example, customer A had a different winner, XGBoost classifier. For customer B, the winner was random forest. So each customer gets the best model for him. What about large customers? So we've talked about how large customers have complex data, complex structure. They have different business units, different teams, a team selling laptops, a different team selling data storage units, and these teams were completely different. They have different leads, and we can't really train the same model for all these teams. So data segmentation comes to the rescue. The customer can actually configure the data segmentation and divide the leads into different segments, different teams. And then we can train multiple models for each segment, for each team, and choose a winner. Again, this time not for a single customer, but for each segment, we choose a winner. What about small customers? So small customers, as I said earlier, don't have enough data for training good models. So we're currently thinking about using global models, combining data from multiple small customers and training a global model on the combined data can have good results for all these customers. If we trained a model separately, it might not result in good results for all of them. Another example I want to give related to training a model is how we tuned our parameters using grid search. So we used for lead scoring, we used XGBoost classifier. Now XGBoost classifier has many different parameters. How do you choose the right combination? There are many parameters. Do you examine all the parameters? So a grid search is a really complicated task. Think about it. We have N customers. If we're examining leads from different times, say 1 month ago, 2 months ago, 3 months ago, etc., we have T different time frames. We have P parameters, and for each parameter of XGBoost, there are V possible values, let's say. So there are endless possibilities here. In a single run, we need to get leads for a particular customer from a particular time frame, train the XGBoost model using a specific configuration, evaluate the model, and finally store the results. This is just a single run, but we need to do that millions of times. We need to execute millions of runs. Even if we choose what we perceive as small numbers for N, T, P, and V, we get millions of runs that we need to execute to examine all these options. So that's not feasible. So how do we approach such a complicated task? So first you have to know your limits. You have to know how many machines you have to execute and how many runs you can actually execute in the time that you have. You can't just grid search forever. So you have time limitations, obviously. You need to know how many runs you can execute. Once you know that, you can start narrowing your search. So you choose subsets of customers, subsets of everything we talked about, the N, the P, the whatever, We choose subsets of parameters, subsets of values, and you can also use a two-level search when it comes to the parameter values, because obviously each parameter has many possibilities for the values that we choose. We can start with widespread values and then tune as we go. And finally, you can think of different optimizations. For example, storing data for reuse between runs. So if we're only changing the XGBoost classifier parameters, and we're not changing the other pipeline steps like feature generation, feature selection that happened before the XGBoost classifier, we can store their outputs and reuse them in the next runs. You should probably also think of a recovery mechanism, and you can also prune bad configurations. So if at some point you identify a configuration as bad, you decide what the point of identification is when you identify a bad configuration, but once you identified a bad configuration, you just no longer examine it.
What is recovery mechanism?
A recovery mechanism means that if the execution suddenly fails, so how do you continue your execution from the last point? Okay? So grid search is obviously very complicated, and you have to think of many things. You have to consider many things when you approach this task. One last thing that I want to mention in the train model phase is that every change that we do, we have to do it carefully. Whether if it's adding a new feature or removing an existing feature, whatever changes we're doing to our model can improve for one customer and harm another. So we have to test everything, and we have to research everything before we just deploy it to production. And we do research it using Jupyter, obviously, and we also use Papermill for executing parameterized notebooks, and we do that in parallel by running multiple processes. After we finish the research phase, we have to make that transition from research to production. You have to make your code production ready. Obviously, many libraries work well in research, but that doesn't mean that I want to use them in production because they're error prone, because it doesn't cover the basics that we've talked about earlier. It doesn't scale well. For example, Pandas is more error prone, so we've decided not to use it in production. And once you've made your code production ready, again, you should have accuracy regression tests in place to prevent deployment if your model is suddenly inaccurate due to the changes that you've made. So a few takeaways here. Obviously, dealing with scale is complicated for any application, but for turnkey AI applications, it's extremely complicated. And you have to think about not a single customer. You have to cover and think about every customer, all your customers from small to large that have different challenges. And you also need to think about the trade-off that we've talked about, trade-off between accuracy and performance. And you have to make your code production ready, and that's not easy. And finally, testing and monitoring is crucial. You should always have performance tests in place, accuracy tests in place to cover the flow. So that's it. Thank you.
Thank you, first of all.
Have you considered using a scalable language such as Scala instead of Python, and a scalable framework such as Apache Spark, for example?
So we're currently using Python and not Scala. I don't know if it's in our roadmap to use Scala, but Python is a good language for AI code, so we're relying on Python right now, and it's working well for us. I don't know if maybe there will be plans in the future. asked you something else. Yeah. So the question was, how do we decide when to retrain our models or how to retrain our models? We actually retrain. There are multiple flows. So first of all, if, as I said before, we allowed the customer to have a certain level of control. So if the customer changes a certain configuration, obviously we retrain, we trigger retrain. So that's one aspect. And another aspect is basically we've learned that in lead scoring, so each product is completely different, but in lead scoring, I think we train every 10 days or so. So we have different retrain times, and we've learned that's enough, and that's good enough for us. Yeah.
Once you...
So we actually, it's really complicated, but what you're asking is if we need to make changes after deployment, how do we do that, and does it affect old releases or previous releases? So in Salesforce, it's really complicated because we actually, in lead scoring, for example, we can make changes to our model and it will affect directly to the customers. We can make changes and we can make changes relatively fast. It will reach the customers pretty soon. But again, it depends. It's a pretty complicated question because it depends which changes and ultimately what we promise for the customers is the most important thing. So we won't break that, and it depends which change we're talking about, obviously. But if it's something, if we identify something we can improve in our model, we can do that usually fast and deploy fast.
But then you need to evaluate if your change improves the customer output or affect him or make it worse.
Of course, every change we make, we have to test it, we have to research it.
Do you know it, or you need the customer to tell you it is okay and it is better for me?
So, do we know if how our changes will affect the customer? So we can know to some extent. We can know by doing this research that I've talked about. We do that before deployment, before the solution reaches our customers. And then we can detect many issues, many problems in the research phase and not harm the customer in any way. But we obviously have a direct connection to the customer. We get customer feedback, and we are able to get feedback from our customers as well.
Actually, it's a very good question, and the answer will be in the next session. How we measure model performance and data quality issues. Exactly.
Yeah. So, any other questions? Okay, so the question is regarding celery tasks. How do we monitor it? How do we prevent them from getting stuck? So, as I said before, we have many monitoring tools that we use, which are really effective, like Datadog and Splunk logs, and we use all these monitoring tools to detect issues if there are any, and then we can solve them.
So monitoring celery